it is the third part of section 8.6, the SOM algorithm and its interpretation. Earlier in the second part, we considered four major steps in SOM: initialization, competition, cooperation, and adaptation. Those steps can be summarized as follows. Okay. In initialization, connection weight WK in D dimension is attached to each unit K, and the value can be initialized with small random values. So the collection of the weight vectors make a weight matrix. Now, for each iteration, we make a sample. So in each iteration, one data point will be chosen. And here, through competition, we try to find the matching unit, that is the winning unit. And here, the correspondingly, the neighborhood function will be defined, and that is a sort of a cooperation, and here updated. This is now adaptation. Okay, this sampling, matching, updating will continue up to the point that the future map stops changing. And that's the algorithm for the SOM. Here, the results of the SOM is now clusters. After learning, cluster CK can be defined as the set of inputs closer to WK than to any other one. So that, in a sense, WK is serving as a centroid of the cluster. So representation. Now the corner map is the representation of the weights or the cluster contents, and here displayed according to the neighborhood structure. And this is one example for data approximation, and it's compared here. The blue line is the first principal component vector from PCA, and this red curve is for one-dimensional SOM. Now, for given data, and SOM seems making good clustering through this curve, and because of the noise points and around there, it's not well matching to the major part. However, it is quite well working, and also it's also a matter of the parameters. If we choose some other algorithm parameters, then you can make better. Now here, the fraction of variance unexplained in this example is 6.86% for SOM and 23.23 for PCA. So variance explained for the PCA is about 77%, and for SOM it's about now 93%. So for this example, once you want to represent the data set, then rather than PCA here, SOM is better. Okay. Here we have properties of the Conan maps. Now that is quantization property. The weights represent the data space as accurately as possible. as do other quantization algorithms. Here, so that its quantization means discretization, so that each here the weight, that one is representing the points surrounding the weight, and in this way it has some quantization property, and also it has a self-organization property. That means that the weight preserves the topology of the data. The close input belong to the same cluster or neighboring clusters, so that once you try to visualize the output, then once the similar, then the points will be in the same cluster or near around. And if it is not in the same cluster, then the clusters will be near each other. Okay. In this way, that topology of the data will be preserved. There are many theoretical issues. I wrote down here many questions. And now when t tends to infinity, that means the number of iteration becomes larger and larger and larger. And we have to consider the convergence issues and also some equilibrium the states. And there are many issues. The reason people are considering these issues is that the convergence is not so clear and not so fast, and also it's not so much stable. So that, and depending on your choice of parameters and depending on your data set, the behavior, the performance can change a lot. So even though you choose slightly more noisier data set, for one data set is working, but slightly noisy data set, then it may not work. In this way, it's quite sensitive to certain the characteristics of the data and also certain parameters. Here in practice, the convergence and the ordering issues here now. Okay, the SOM algorithm may start from an initial state of complete disorder, and it will gradually lead to an organized representation of activation patterns from the input space. So in the beginning, yes, organizing or ordering phase will be there. And so and later on, now it changes into convergence phase. For ordering and self-organizing phase, now here it requires typically here at least 1,000 iterations, and so that it takes really a long time. And you need a very careful the choice of the parameters and now neighborhood functions and so on. So if you do it carelessly, then you cannot get here good organizing phase. And for convergence phase, even this is slower. Typically, the number of iterations in this phase will be at least 500 times the number of neurons in the network. If we choose about 20 neurons in the network, then that means that at least 10,000 iteration is required. So that here quite slow, and usually slow algorithms diverge more easily. So once it's converging very fast, then divergence is not frequently happen. But if your algorithm is slow, then now it can diverge, or it can be oscillatory later on. In practice, the algorithm is not easy to handle. However, once you have good self-organizing phase and convergence phase, so that you can get good convergent result, then that is quite good for understanding the data, and also quite good for visualizing the key components in the data set. So that's the reason people enjoy SOM. Okay, this is end of the section and end of the chapter. Thank you.